In this talk, I shall be outlining some recent results on the satisfiability problem for fluted logic with counting quantifiers, a large fragment of first-order logic whose satisfiability problem is, as I shall show, decidable. This is joint work with Lydia Tendera. I begin with some background on the fluted fragment and proceed to define its extension with counting quantifiers. I shall then explain the main ideas behind the proof that the satisfiability problem for this fragment is decidable and conclude with some open questions. The fluted fragment is actually quite old and dates back to the work of W.V. Quine in the 1960s. Very roughly, the idea is that variables are quantified in the order in which they appear as arguments of predicates. Here are some examples. So we see no student admires every professor, and no lecturer introduces any professor to every student. Just straightforward formulas of first-order logic. More precisely, we consider the fragment of first-order logic in which all atoms are of the form shown here, a non-logical predicate followed by a contiguous sequence of numbered variables as arguments. Boolean combinations can be formed from formulas only when their last free variable is the same, and only the last free variable of a formula may be quantified. Thus, equality, individual constants, and function symbols are not present. We call the resulting system the fluted fragment, abbreviated FL. We denote its M variable subfragment by FL superscript M. We remark that the earliest definitions of this fragment were given within the framework of predicate functor logic, where it emerges naturally by prohibiting operators concerned with the permutation and duplication of variables. We can see better what's happening with the fluted fragment by considering an example. So here I have a formula, fluted formula. It's quantifier free, that's okay. You notice that this atomic formula here has a contiguous sequence of variables as its arguments. That's fine. This one too, just one. We can form a Boolean combination because the last free variable is the same. And I've drawn the same formula over here, except that I've lined things up so that the variables x3, the last arguments, are lined up in a column. Now I can quantify the last free variable, and so I've done that, and I've drawn the quantifier here, all lined up. The last free variable is now x2, so I can combine this with any fluted formula whose last free variable is x2, for example, this fluted formula here. And I've drawn that again in a column so that the last free variables are lined up. And we can quantify this last free variable, this time existentially. And now I can combine this in a Boolean combination with any fluted formula whose last free variable is x1, because that's the last free variable here. And I've done that here. And again, I've lined up, I've just drawn exactly the same formula here in this diagram, but with the variable x1 lined up. And now I can quantify x1, and you see that the x1, x2, and x3 form nice columns like this, and this is supposed to remind us of the architectural decoration known as fluting, hence the name fluted fragment. A few historical marks are perhaps in order here. The original idea of restricting the order of occurrence of variables in formulas stems from Quine's homogeneous M-adic formulas, roughly what we are calling the fluted fragment, but with all predicates having the same arity. So it's much less interesting than the fluted fragment as we've defined it. This was later generalized to the fluted fragment. The term was originally Quine's, which was presented within the variable-free framework of predicate functor logic, as I mentioned. Quine never presented a formal proof of decidability, of satisfiability, though his work was discussed by later commentators, most notably William Purdy, who gave a reconstruction of the fluted fragment. Now, I went back to the sources, and it doesn't seem to me that Purdy's reconstruction is faithful to Quine's original definition. Nevertheless, it's Purdy's definition which has established itself, and indeed which is, it's fair to say, from the point of view of recent work in computational logic, of greater interest. So that's how we shall be using the term here. The satisfiability problem for any logic L is the following problem. Given a formula of L, determine whether it's satisfiable, has a model. The finite satisfiability problem is the problem, given a formula of L, determine whether it's finitely satisfiable, i.e. has a finite model. A logic L has the finite model property if every satisfiable formula is finitely satisfiable, i.e. if these two problems coincide. Purdy showed that his and our fluted fragment has the finite model property and that the satisfiability problem is decidable. In fact, it can be shown that the m variable subfragment of the fluted fragment is m minus 2 nx is in n minus 2 nx time for all m greater than or equal to 3 and is m divided by 2 rounded down nx time hard. Hence, the satisfiability problem for the fluted fragment as a whole is tower complete in the system of trans-elementary complexity classes due to Sylvain-Schmidt. The next section deals with the addition of counting quantifiers to the fluted fragment. The fluted fragment with counting, abbreviated FLC, is the obvious extension of the fluted fragment with counting quantifiers. Counting quantifiers here are expressions of the form there exist at least, at most, or exactly m x such that ... And while we're at it, we've also added the equality predicate. Remember that the fluted fragment as defined doesn't have equality, but we might as well add it since we're adding counting quantifiers anyway. So we'll call the resulting fragment the fluted fragment with counting. So here are some examples. As you see, it's pretty much as you expect. At most, 3 lecturers introduce a professor to at least 5 students. You'll see that this is indeed fluted. I mean, the same rules for fluting apply as before, right? So the arguments to predicates have to be contiguous sequences. You perform Boolean combinations only when the last variables are the same, and you quantify the last variable only, but this time you're allowed counting quantifiers. And we have equality as well, so every absent-minded professor introduces some student to himself is also fluted. Again, if you look at this last formula, you'll see that the arguments to predicates are all in order and everything's as it should be, so it's fluted. And as before, we denote, of course, the m variable subfragment with the m superscript. We shall additionally consider the semi-fluted fragment with counting, abbreviated SFC, in which the fluting restriction is waived for subformulas with at most 2 variables. So this fragment arises as a byproduct of the satisfiability checking procedure for the fluted fragment with counting outlined below. So it's something we get for free. We denote its m variable subfragment again with a superscript, and we remark that the 2 variable semi-fluted fragment with counting coincides with C2, the 2 variable fragment of first order logic with counting quantifiers. In other words, when you've only got 2 variables, there are no fluting restrictions at all. You can have the variables in any order you like. You can have repeated variables, no restrictions. So it's with just 2 variables, it's simply the logic known as C2. It's known that the logic C2 lacks the finite model property, but its satisfiability and finite satisfiability problems are both decidable. In fact, they're nx time complete. And here are some, originally due to Grade et al. And Pocholsky et al. Simultaneously, some references here. So now we can state the main results of this paper. So theorem. The fluted logic with counting retains the finite model property. and the satisfiability problem for its m variable subfragment is in m-1 nx time for m greater than or equal to 2. The satisfiability problem for the m variable subfragment of the semi-fluted fragment with counting, as well as its finite satisfiability problem, are in m+2 nx time. And the best lower bound for these logics is m divided by 2 nx time hard. So quite a gap. This is quite something of a yawning gap that opens up as m gets large. So we remark that at this point that fluting enables us to eliminate variables entirely. So what do I mean by eliminating variables? Well, here are some examples of fluted logic with counting. It doesn't really matter here whether you've got counting or not. There's nice fluted logic, and here are the variables. I've illustrated them in blue. Well, when you think about it, they don't really contain any information at all. So we could just eliminate them. I mean, you can reconstruct them. Since you know that the sequence is continuous, Boolean combinations have to end with the last same free variable. You have to quantify the last free variable. You can always reconstruct these with a little effort. And in fact, as long as you know the arity of every predicate, you don't even need to remember what those are because it's kind of built into the predicate. So you can write fluted formulas now completely without variables, and that's what we'll do in the sequel. It's a little bit more compact. It also has the advantage that variants of the same formula are lexically identical, and that makes actually some of the proofs a little bit easier to navigate. We now come to a sketch of the proof ideas. We begin with the normal form lemma. Given a formula of the m+1 variable subfragment of fluted logic with counting, we can compute, in polynomial time, one of the form displayed here, satisfiable over the same domains. We're employing variable-free notation. Here, for all superscript m stands for a block of m universal quantifiers. The formulas mu s and nu t are quantifier-free fluted formulas of arity m, and zeta s, eta t, and theta are quantifier-free fluted formulas of arity m+1. Thus, normal form formulas are flat. There's at most one quantifier alternation, and this makes it easy to see what's going on when we're reasoning about models of formulas. So this is a fairly standard normal form formula that many of you will be familiar with. Of course, we've written it with variable-free notation here. Another useful notion when reasoning about fluted logic is that of a fluted M-type, namely a maximal consistent set of fluted atomic formulas, or a maximal consistent conjunction of fluted atomic formulas and their negations, involving predicates of arity at most m. So here's such a formula. All of these predicates involve arity at most m, and so we have a maximal consistent conjunction of such atomic formulas. Any m-tuple of elements in a structure interpreting the relevant signature satisfies a unique fluted M-type in that structure. Notice that if a predicate, say P1, has arity strictly less than m, then it's the suffix of the tuple that the predicate's applied to, not the prefix. Fluted M-types don't see relations involving proper prefixes of the tuple. Now, we begin with an easy case, and that is the following lemma. If phi is a satisfiable formula of the two-variable fluted logic with counting, then phi has a model of size bounded by an exponential number of the exponential function of the number of symbols in phi. And the satisfiability problem for this fragment, therefore, is in nx time. Formulas, remember, using the normal form lemma look like this. So mu s is now a one-place quantifier-free formula, zeta s two-place quantifier-free formulas. And the proof is very, very simple, right? Given any model of such a formula, we look at each fluted one type in turn. select a small number of representatives to serve as witnesses, and we delete everything else. Now, if we have a random element of this structure requiring one of these one types as a witness, let's suppose this element satisfies various mu s's, and therefore it requires various witnesses, some of which might have one type of pi, and they might have been deleted. Well, in that case, no problem. We can just choose one of the survivors and reset that fluted one type so it acts as a witness. And we'll have enough witnesses to go around, provided we take a reasonable number. In this way, we can reduce the number of elements of any particular fluted one type in a structure, and therefore the size of the whole structure. And the proof is really extremely easy. We cannot do this without fluting. The two-variable fragment with counting quantifiers but without fluting lacks the finite model property. Here's a typical example. We have a formula which says the binary relation R. There's an object with no predecessors. Everything has a successor, and everything has at most one predecessor. It's well known that this formula has models but no finite models, and so what I just did, you can't do without fluting. So the two-variable fragment without fluting certainly doesn't have the finite model property. The satisfiability and finite satisfiability are still in nx time, but those are actually quite hard results, not nearly so simple as with fluting. Now, our strategy is to reduce the satisfiability problem for FLC m+1 to that for FLC m, possibly with an exponential blow-up. We may as well start with a normal form formula in FLC m+1. After all, we have a normal form lemma. What we want to do is to manufacture a formula in FLC m satisfiable over the same domains. Now, suppose we have a model of this normal form formula, and let's take any m tuple of elements in this model. I'll write such an m tuple as a bar, where a bar is an m-1 tuple. And you'll see in a moment why I do this. But it's just an m tuple of elements. That m tuple will satisfy various of these conditions mu s. It follows from these conjuncts that there will be various witnesses b, such that the m+1 tuple a bar b satisfies the corresponding formulas zeta s as mandated by the counting quantifiers. So various witnesses are now required. Let's draw a picture of these witnesses. Here we have a bar, so that's an m tuple, and we have various witnesses as required by the counting quantifiers. If you take any of these m+1 types, a bar b, that will have a fluted. If you take any of these m+1 tuples, a bar b, that will have a fluted m+1 type. And therefore, the tuple a bar determines a multiset of fluted m+1 types, as required by the counting quantifiers. And what the counting quantifiers do is to impose a system of linear constraints on that multiset. So they, more precisely, the counting quantifiers impose a system of linear constraints on the multiplicities with which every fluted m+1 type may appear in this multiset. The idea behind the reduction is that we introduce new Emery predicates to identify these witnesses. More precisely, the new Emery predicates relate the m-1 tuple A to the witnesses B. Thus, A bar, which is an m-1 tuple, is associated with a multiset now of fluted m types, just as a bar is associated with a multiset of fluted m+1 types. And the work of the proof is to formulate a corresponding system of linear constraints on the multiset of fluted m types, depicted in dark red, such that any m-1 tuple A in a structure for which these conditions are satisfied can be expanded by interpreting various m+1 predicates in such a way that the multiset of fluted m+1 types corresponding to a bar satisfies the original constraints. So from the original formula, we have a system of linear constraints on the fluted m+1 types corresponding to the m tuple A bar, together with its witnesses. We then introduce additional predicates, as it were, to identify these witnesses, and formulate a system of linear constraints on these new witnesses, but these are constraints on a multiset of M types. In other words, we forget about the element A. And the work of the proof involves ensuring that these reformulated linear constraints on multisets of fluted M types are such that we can reconstruct the original multisets of fluted m+1 types in such a way as to satisfy the conjuncts of the original formula. And of course, systems of linear constraints on fluted M types can be formulated in a using a formula of using a formula of the M variable fragment of fluted logic with counting, because we now have only M types, multisets of M types. So this allows us to reduce the satisfiability problem for m+1 variable fragment of fluted logic with counting to that for the M variable fragment of fluted logic with counting. Though there may be, by repeating this reduction, we obtain an instance of the problem, the satisfiability problem for 2 variable fluted logic with counting, which of course, by the lemma we just mentioned, is certainly decidable. So this is enough to show the decidability, finite model property of m+1 variable fragment of fluted logic with counting, and obtain bounds on the complexity of satisfiability. Now, when you think about the reduction, the only predicates that are affected as you manipulate the formulas are predicates of maximum arity. In other words, predicates of arity 2 are completely left alone as you're reducing m+1 to m, all the way down back to the 2 variable fragment of fluted logic with counting. Predicates of arity m are simply left alone. So we obtain an easy generalization to semi-fluted logic, where, remember, the restriction to fluted formulas is lifted for formulas with 2 variables and predicates of arity 2 for that fragment. And that's basically it. Conclusions. We've shown that the M variable, I'm sorry, I'll start again. We've shown that the satisfiability problem for the m+1 variable subfragment of fluted logic with counting is in m(nx) time for all m greater than or equal to 1. Actually, taking 0 nx time to be np time, this is actually true also for m equals 0 when you think about it, but it's by the by. As a byproduct, we've observed that the whole of the 2 variable fragments can be added to fluted logic with counting without losing decidability of satisfiability, though of course we do lose the finite model property. In terms of further work, I mentioned just 2 matters here. In order to obtain the complexity bounds given, one needs to liberalize the notion of counting quantifiers slightly. Any M tuple of elements realizes a multiset of fluted m+1 types, as explained. What counting quantifiers do is to impose constraints on that multiset. But then one can consider super counting quantifiers, imposing almost any computable collection of constraints on these multisets of fluted m+1 type. And the maximum possible extent of this liberalization is as yet unclear. Secondly, and more concretely, one might tackle the gap between upper and lower complexity bounds, which is simply yawning for large values of m. Such a gap exists even for the fluted fragment without counting, and the present speaker has so far failed to close it.